Welcome to our recorded session for Air Conditioning Diagnostics Module number 1 and 2. Today we're going to be learning and reviewing the diagnostic procedures for both R410A and R22 air conditioning systems. Some of our key learning objectives will be as follows. We're going to review the refrigeration cycle and the graphics. We're going to talk about expansion valve and have an overview. We'll talk about pistons and orifices and other types of metering devices specific to a fixed type of metering device, saturation temperature pressure chart overview and practice, and we're going to talk about evaporator loading and system pressures. So this time let's review our R22 refrigeration cycle with a piston or an orifice. Please notice in the middle of the screen you have a suction gauge displayed and a liquid pressure gauge displayed. Later on in our program, we'll activate those gauges, but for the time being, just know that the suction will be on the left, it's the blue gauge, and the high side or the liquid pressure is on the right, that'll be the red gauge. Also, please notice if it's an R22 service call. If it's an R22 service call, the background of the gauges will be white. However, if it's a 410A service call, the background will be pink or rose colored. Now, in the lower left-hand corner of the screen, starting at the compressor, if you'll notice we have a hot gas line from the compressor. You'll also notice arrows throughout the refrigeration circuit indicating the direction of refrigerant flow. So from the compressor, we have a hot gas line going to the outdoor coil, where the hot gas is condensed into a liquid. It then passes through a filter dryer and down a liquid line. Once it reaches the orifice or TXV, the orifice or TXV will spray that liquid refrigerant into the indoor coil, also known as the evaporator, and it will boil that refrigerant into a cool vapor. That cool vapor will then go down the suction line back to the compressor. This is the normal refrigeration cycle for an air conditioning system. Again, team, please notice that the R22 service calls will have a white background on the gauges. Now let's take a look at the 410A service call. You'll notice on the 410A service call, we've put a TXV in the refrigeration circuit, but that's okay. It's going to serve the same function as the piston in the fact it will meter or spray refrigerant into the evaporator coil and meter refrigerant into the indoor coil. Please notice the refrigeration cycle remains the same. The hot gas line is still the same, and the outdoor coil, the condenser coil is still the same, and so on. But please notice also the 410A service calls will feature a pink or a rose-colored background on the gauges indicating it's a 410A service call. At this time, let's talk a little bit about the expansion valve or the TXV. Please notice as you take a look at the graphic that you have liquid coming in from the left-hand side on the liquid line into the valve assembly. The liquid will then pass over a valve and seat assembly and will be metered into the evaporator coil. Notice on the outlet of the evaporator coil on the suction line there's a sensing bulb. That sensing bulb has a refrigerant in it. Now it may or may not be the same type of refrigerant that's in the system. You'll notice that it's a completely sealed system. So the sensing bulb has a refrigerant in it, and it will sense the temperature of the suction line leaving the evaporator coil. When the sensing bulb warms up, it will exert pressure on the top of the diaphragm, forcing the valve open by way of the push rod or push rods that may have more than one. As we open the valve up, we'll meter more refrigerant into the evaporator coil, and the coil will start cooling down. As the evaporator coil cools down, the suction line leaving the evaporator coil will also cool down and cool the sensing bulb. As we cool the sensing bulb down, it will ease the pressure up on the diaphragm, and the spring tension on the underside of the valve assembly will start to close the valve off. As the valve closes off, it'll meter less refrigerant into the evaporator coil. It'll start to warm up a little bit, and as a result, the sensing bulb will exert more pressure on top of the diaphragm and open the valve up a little bit. And so back and forth it goes between opening and closing based on the temperature of the sensing bulb. In addition, to smooth the expansion valve out and to prevent erratic operation, we're going to take suction pressure from the outlet of the evaporator coil on the external equalizer line and place that suction pressure to the underside of the diaphragm. That will result in an expansion valve that's actually a lot smoother and not only smoother, but also will meter refrigerant more reliably. It should be noted an expansion valve is the best type of refrigerant control available on a refrigeration circuit. It does have some moving parts. There is a degree of complexity with it. However, it's the best for refrigerant control. In addition, the expansion valve will maintain a constant flow rate into the evaporator coil as the heat load changes on the evaporator coil. So as it gets warm in the house, to give an example, or in the structure, the valve will open up and meter the proper amount of refrigerant. In addition, as the house cools down or the space starts cooling down, the evaporator will cool down and it will ease up the pressure on the top of the diaphragm on the expansion valve and feed less refrigerant into the coil. Now, it should be noted, please write this down on your handout or write this down and remember it. The expansion valve under normal nominal operating conditions should maintain about 10 to 15 degrees of superheat under normal running conditions. Another type of metering device that's very common in our industry is called an orifice or a piston type of metering device. The orifice or piston metering device is an extremely simple device. It's simply nothing more than a piece of brass with a hole drilled in it. You'll notice that the assembly, as you take a look at your graphic at this time, you'll notice a liquid line adapter bolts onto the body or to the distributor that feeds the evaporator coil. Inside that assembly, you'll find the orifice or the piston. Now, please note that the piston has a tapered end on one end. It has to go towards the body of the distributor. Now, it should be noted that the orifice or the piston type of metering device is a type of metering device that's fixed. It does not move. It has a fixed orifice. And it should be noted that the proper way to charge a system with a piston or an orifice will be by way of a superheat charging chart, which we'll review shortly. So remember, again, on an expansion valve, it should maintain approximately 10 to 15 degrees of superheat. In addition, from a charging standpoint, the expansion valve will always be used with a subcooling type of charging. Subcooling for charging with an expansion valve. However, on the piston type of metering device, we're going to have to utilize a chart, a superheat chart, to charge it properly with a piston. So at this time, team, let's go ahead and review our saturation temperature pressure chart. So if you'll please take your pressure temperature chart and follow along as we take a look at using the pressure temperature chart. Now remember, team, the pressure temperature chart tells us the temperature that the refrigerant is changing state in the coils. So not only are we going to convert pressure to temperature, but we're also going to imagine or think about the temperature, not only the temperature, but also the state of the refrigerant as it changes state in the coils. Putting it another way, quite frankly, in the condenser coil, the temperature that the hot gas turns back into a liquid is what we call saturation temperature. In addition, in the evaporator, the temperature at which the liquid refrigerant that has been metered past the metering device into the evaporator, the temperature with which that liquid boils back into a cool vapor is saturation temperature as well. So from an explanation standpoint, saturation temperature is the temperature of the liquid or the vapor refrigerant at any given pressure, where if we add or remove any heat energy, we get a change of state from liquid to a vapor in the evaporator, from a hot gas to a liquid in the condenser. So when we look at the pressure temperature chart, we should be thinking about what temperature is the refrigerant changing state in the coils. So referring to your R410A section of your pressure temperature chart, let's do some examples together. So we'll notice at 55 pounds of pressure, 55 psi-G, on the 410A chart, please find the pressure temperature conversion off the chart. It should be 5 degrees. Let's do another one. At 130 psi-G, R410A, what's the pressure temperature conversion? That is correct, 45 degrees. At 265 pounds of pressure, help me out. At 265, what is the temperature that refrigerant is changing state in the condenser coil? That is correct, 87 degrees. At 375 pounds of pressure, 410A, tell me, what is the pressure temperature conversion? Good, 112 degrees is correct. At 455 pounds of pressure, what is the pressure temperature conversion? In other words, at what temperature is that hot gas turning back into a liquid in the condenser coil? That is correct, 127 degrees Fahrenheit. So as you review your pressure temperature chart, please remember there will always be a pressure temperature conversion off the chart, and it really is telling us at what temperature the refrigerant is changing state in the coils. Let's do some R22 practice at the bottom of your screen at this time. At 35 pounds of pressure for R22, what's the pressure temperature conversion? Good, 13 degrees. At 68 pounds of pressure, what's the pressure temperature conversion? That is correct, 40 degrees. In other words, at 40 degrees, the refrigerant inside the evaporator is boiling off into a cool vapor at saturation temperature. Let's do another one. At 85 pounds of pressure, what is the pressure temperature conversion for R22? Good, that's correct. At 51 degrees, the temperature and the pressure conversion line up on the chart. At 230 pounds of pressure for R22, tell me, team, at what temperature is that hot gas turning back into a liquid in the condenser? That is correct, 111 degrees. Now remember, team, it's very, very important that if you're within 1 or 2 degrees of the chart, that's close enough for field work. Let's do a final example. At 325 pounds of pressure for R22, at what temperature is that refrigerant turning back into a liquid in the condenser coil, that hot gas? That is correct, 137 degrees. So this time, please review the chart and make sure you're comfortable with it. And by all means, please review this recording or this session again, this portion of it, for chart review and pressure temperature chart practice if you have any further questions or comments. Okay, at this time, let's talk a little bit about evaporator thermal loading and system pressures. You'll notice on the left-hand side we're graphically showing molecules kind of moving slowly within the tubes of the evaporator. And on the right-hand side, we see that we have really vigorous molecules moving fast at a higher pressure in the evaporator coil. And this is an important thermodynamic concept, team. Remember, if the evaporator has low heat load on it, in other words, there's not a lot of heat energy being absorbed into the evaporator, what's going to happen is the pressures will be low. If we have a lot of heat energy being absorbed into the refrigerant in the evaporator coil, the heat energy will be high, and as a result of a high heat energy, we'll also have a high pressure. So there will always be a pressure-temperature relationship between the amount of heat energy that's being absorbed in the evaporator and the pressures in the system. Now, it should be noted in the middle of the screen, you'll see there's a 400 CFM per ton, a little flashing text. Now, this is just to remind you that we always want to design our duct systems for 400 CFM per ton of cooling capacity of the outdoor unit. So in other words, if we have a 2-ton unit outside, we want to make sure and deliver at least 800 CFM cooling airflow. If we have a 3-ton unit outside, it would be 1200 CFM, and so on. Now, it should be noted the evaporator is what drives the pressures in the system. If the evaporator has low temperature, it's at a low temperature and it's absorbing very little heat, the pressures in the system will be low. If we have a lot of heat energy on the evaporator, the temperatures and the pressures will be high in the system. Now, some reasons we'd have low heat load on the evaporator coil, some classic examples would be a dirty air filter, a dirty evaporator, perhaps an undersized return duct, or possibly a return duct system that's collapsed, or maybe it's even on the wrong fan speed. So it's very, very important that we have to deliver the proper CFM or the airflow in a air conditioning system if we want to expect proper performance. That concludes module number 1. And so the basic concepts that we looked at in module number 1, again, refrigeration cycle and expansion valves and metering devices. And we also reviewed the fact that you have to have proper heat energy being absorbed into the evaporator for proper system operation. So this time, let's go ahead and transition into air conditioning diagnostics module number 2 at this time. Okay, so again, welcome to the program today, and we will be learning and reviewing some diagnostic procedures specific for 410A and R22 air conditioning systems. Some of our key learning objectives today will be review of the quick start kit, also called a hard start kit, using the sling or digital psychrometer to find wet bulb, dry bulb, and relative humidity of the return air going into the unit, and reviewing superheat charging chart and some practice of that superheat charging chart. Now please remember, team, whenever we have a piston on the indoor coil, we'll need to utilize the superheat charging chart. So at this time, let's go ahead and review a quick start kit. If you'll look at your handout, you should have a handout with your book or your handout. And you'll notice you can read the text fields. And you'll notice that the quick start kit will be utilized if we have a compressor that's having a hard time starting. Now, some reasons a compressor may have a hard time starting would be low voltage on the job site, a very long line set, a line set that has a lot of vertical lift, or we may just have a compressor that's a little bit tight. So it's important that we understand a quick start kit will not damage a compressor as long as it's applied properly and it's properly sized. So looking at the block diagram, we see that we have power L1 and L2 going into the compressor, common and run terminals. In addition, we have a run capacitor that's permanently wired between the start terminal and the same power source or the same side of the line that's feeding the run terminal. Now, when we put a hard start kit on our quick start kit, also called a quick start kit, we're installing an additional start capacitor and a potential relay. You'll notice the potential relay, terminal number 1 and terminal number 2, there's a set of contacts that are normally closed when the unit is not running on the potential relay. You'll notice terminal number 5 on the potential relay is actually the other side of a coil that goes between the common terminal and terminal number 2, the start terminal. You'll notice the start capacitor is wired in parallel with the run capacitor. One side of the start capacitor goes to the same side of the line that goes to the run terminal, but also the same side of the line that's feeding one side of the run capacitor. The other side of the start capacitor goes to terminal number 1 on the potential relay. Now, once we start the compressor and the motor starts to come up to speed, we'll actually generate what's called back EMF, or a voltage on the start winding. That start winding voltage oftentimes is 1.5 to 2 times higher than line voltage. But we can use that high start winding voltage to energize a potential relay coil between terminals number 2 and 5, and we will open, once the motor comes up to speed, we'll then open the potential relay contacts between terminals number 1 and 2 and take the start capacitor out of the circuit. Now, this is important. After the compressor starts, we have to remove the start capacitor from the circuit, because if we don't, it can overheat the compressor, it can burn up the start winding, or cause other electrical damage. In addition, it should be noted, the start capacitor is not rated to stay in the circuit all the time. If you'll notice the voltage rating on the start capacitor, it may be as low as 200 or 250 volt AC. However, the start winding voltage can exceed 400 volts when the motor is coming up to full speed. You'll notice on the run capacitor, if you look at the ratings on the run capacitor, they are typically 370 volt or 440 volt rating. This is because they stay in the circuit all the time and the start winding voltage will not harm the run capacitor. Please note also the contacts are open during running operation of the compressor. They have to remain open on the potential relay. At this time, we're going to go ahead and review the digital and the sling psychrometer. The sling and digital psychrometer are actually devices that are going to measure wet bulb temperature, dry bulb temperature, and relative humidity. This will be very important as we start looking at superheat charging charts and other important temperatures on the air side of our air conditioning system. So to use the sling psychrometer, the first thing we need to do is we need to find which thermometer has the cotton wick on it. We'll then completely saturate and soak that cotton wick with water, and that becomes our wet bulb. In addition, you'll notice that we'll read that wet bulb temperature on the thermometer that has the wet bulb or the wick on it. The sling psychrometer also gives us a dry bulb temperature, and you'll please notice that the thermometer on the sling psychrometer that does not have the wick on it, that bulb is dry, and that's referred to as the dry bulb thermometer. We then take the sling psychrometer after we wet it down and we spin it vigorously for about 1 minute in front of the return air grills. If we have more than one return air grill, please remember, team, you're going to want to do it at each return grill and then average the wet bulb and the dry bulb temperatures. We then take the sling psychrometer and we put it back together, we slide it back together, and we align the wet bulb line on top with the dry bulb line in the middle sliding scale. Once we do that, you'll notice that there's an additional line on the sling psychrometer that has a Y. You'll notice the small y where it aligns and reflects a measurement on the relative humidity scale. This is where we find our relative humidity. So in our example, we have approximately 64 degree wet bulb. We have approximately 75 degree dry bulb in our picture on the example. And our relative humidity is approximately 52% relative humidity in this example. Another device that's extremely handy for finding wet bulb, dry bulb, and relative humidity is what we call a digital psychrometer. A digital psychrometer is a device that's going to give you wet bulb and dry bulb temperatures, and they'll normally be found in a window displayed on the digital psychrometer. In addition, the digital psychrometer will also show you relative humidity of the sample or the air sample that it's taking at the return air grill. Now remember, team, don't forget to remove the cap off the top of this digital psychrometer and just set it at the return grill and let it set there for about a minute to stabilize. And then you can read wet bulb and dry bulb and relative humidity. Please note also on the digital psychrometer there's going to be a button of some type to allow you to cycle between wet bulb and dry bulb and other functions. So learn your tool well. In our example, we have a UEI, but there's lots of manufacturers out there. Fluke, a UEI, a Field Piece are just a few examples of manufacturers that make this tool. It's very, very important if you hope to properly charge a system utilizing the superheat charging chart with a piston on the indoor coil, you have to be able to find wet bulb, dry bulb, and relative humidity. At this time, we're going to go ahead and review the superheat chart. Now remember, team, pull out your superheat chart and look at the text field at the bottom of the chart. You'll notice that a superheat chart is only for a piston or an orifice type of metering device. And if you utilize this on a heat pump, don't forget to utilize this chart in the cooling mode of operation. And if it's on a straight air conditioning system, then it will be just a direct correlation. Now please notice that in the upper part of this chart, there's a text box that says diagonal lines represent indoor return air dry bulb, which are the blue numbers, and wet bulb, which are the red numbers. Please note also if the relative humidity is above 70% or below 20%, use the red wet bulb line. As you take a look at the left-hand side of the chart, on the far left-hand side, you'll notice there are some numbers, 50, 45, 40, and so on, down to 5. That is the superheat portion of the chart. Along the bottom of the chart, you'll notice that there's 60, 65, 70, all the way up to 110 degrees. That represents outdoor air temperature. Please notice the diagonal lines in the middle of the chart. Each correspond with a green temperature block that has two temperatures in it. A dry bulb temperature, that's the blue number, and a wet bulb temperature, that's the red number. So the diagonal lines represent indoor return air temperature. So to utilize the chart, step number 1, we have to find outdoor air temperature. So let's do an example together. So step number one, we find outdoor temperature at the bottom of the chart, and in our example, we see it's 90 degrees. We then go to our return air with our sling or digital psychrometer, and we measure the return air wet bulb and dry bulb temperature and the relative humidity to determine if we're going to use the dry bulb, the blue numbers, or the wet bulb, the red numbers. So in our example, let's say, for instance, we have 90 degrees outside, and we have 55% relative humidity. So we'll be using blue numbers. And we see we have 55% relative humidity, and it's 80 degree return air temperature. 80 degree return air temperature in our example. We then follow the diagonal line down until it intersects the outdoor temperature of 90 degrees. And where those two lines intersect in our example, we move straight to the left, and we see that our required superheat in this example is 13 degrees of superheat. So remember, team, as we look at these temperatures, we have to have a digital or sling psychrometer to find wet bulb, dry bulb, and relative humidity. In addition, we need to be able to accurately measure outdoor air temperature. Let's go ahead and clear the chart at this time, and let's do some examples together. And follow along on the chart with your handout as we do some examples together. Let's say in this second example, or this next example, we have a 75% relative humidity in the space. So we automatically know we're going to be looking at one of the red wet bulb numbers, 75% relative humidity. So in this next example, we have 67 degree wet bulb. So please find that line, that diagonal line that corresponds to 67 degree wet bulb. And let's say it's 95 degrees outside with a 67 degree wet bulb. If we move straight to the left, we see the required superheat in that example is 10 degrees. Now remember, team, this chart is going to be used only for a piston or an orifice type of metering device, or a heat pump with a piston or an orifice metering device on the indoor coil in the cooling mode. Now this is a generic chart, and it does work for any piece of equipment or any manufacturer's piece of equipment that has a piston on the indoor coil or an orifice on the indoor coil. Again, this is not a champion chart per se. It's a generic chart that I developed for our training program. However, it's extremely accurate, typically within 2 or 3 degrees of the manufacturers that I've checked it against. So let's do one more example before we conclude with our superheat chart examples. Let's say in this final example we have a 30% relative humidity. Let's say we're in Albuquerque, New Mexico. We have 30% relative humidity in the summertime. So 30% relative humidity, and we have an 85 degree return air temperature. 85 degree return air temperature with a 30% relative humidity. So we'd be using the blue dry bulb line. So please find 85 degree and with a 30% relative humidity, that would give us 85 degree temperature on our indoor return air temperature. And in our example, it's 105 degrees outside. So 85 degree return air temperature, dry bulb temperature, 105 degrees outside. If we find where those two lines correspond or where they correlate together and they intersect, we see that our superheat in that example should be about 12 to 13 degrees. A couple final notes, team, on this particular chart. Remember, always charge the unit within about 2 degrees of what's displayed from the superheat. So plus or minus about 2 degrees is acceptable. And never charge a unit below 5 degrees of superheat. The reason is if you charge below 5 degrees of superheat, you risk slugging the compressor with liquid, and as a result, you can wash the bearings out on the compressor and cause damage. So never charge below 5 degrees of superheat, and always charge within a couple degrees, 1 or 2 degrees from the chart value. Plus or minus is close enough for all field work. I want to thank you very much for your attendance today. Thank you for attending and listening to our recorded session. And by all means, please call me or any of my team members if you have further questions on your champion team. Thank you, and have a great day.